All right, welcome back. Today we're going to be detectives. We're on a mission to solve a mystery that has huge implications for the future of clean energy. The big question is, how do you know a fuel cell is in trouble before it's too late? Let's dive deep inside a fuel cell stack and see if we can decode the signals. Now, this seems like a pretty simple question, right? But the answer is, well, it's a lot more complicated than you'd think. See, a fuel cell stack isn't just one thing. It's made up of many, many individual cells all working together. If just one of those cells starts to struggle, it can bring the whole system down. The real challenge is, how do you hear that one quiet cry for help in a really big crowd? You know, for a long time, the main way to check a fuel cell's health was to just look at the total voltage. It's kind of like looking at a forest from an airplane. You get the big picture, you can see if the whole forest is healthy, but you're going to miss that one sick tree. That's where cell voltage monitoring, or CVM, comes in. It's like having a dedicated sensor on every single tree, letting you spot those hidden problems the view from above would completely miss. So, what kinds of problems are we even looking for? Well, one of the biggest headaches for a fuel cell is managing water. It's a classic Goldilocks dilemma. You can't have too much, you can't have too little. The amount of water has to be, you guessed it, just right. And this slide right here shows you why it's such a dilemma. You've got two completely opposite problems, but they both lead to the same bad outcome. If there's too much water, that's called flooding, it literally blocks the fuel from getting where it needs to go. But if there's too little water, we call that dry out, the internal resistance just skyrockets. Either way, performance tanks, and you risk doing permanent damage to the cell. So, how do we solve this tricky Goldilocks problem? We need to listen. We need to listen really closely to the voltage signals coming from deep inside that stack. And this is where our high-tech diagnostic tool, CVM, really gets to shine. The key thing to understand about CVM is that it's like giving a doctor a stethoscope for every single cell in the stack. Instead of just taking a general temperature of the whole system, we're listening to each individual heartbeat, and we're doing it in real time. This lets us catch what's called non-uniform behavior. That's when one cell is struggling while its neighbors seem perfectly fine. Okay, so just like a doctor looks for specific vital signs, CVM gives us 3 key metrics. Think of them as 3 critical clues that help us decode what's really going on inside that fuel cell. Our first clue is the mean CVM. This one's pretty straightforward. It's the average voltage of all the cells put together. You can think of it as the overall health score, or the final grade for the entire class. It gives us a good general sense of how things are going. Now, clue number 2 is the min CVM. This is the voltage of the single worst performing cell in the entire stack. This is our canary in the coal mine. It's an incredibly sensitive indicator that tells us about the health of the absolute weakest link in the chain. But our third clue is the real game changer. It's called delta, and it's super simple. It's just the difference between the average voltage and that minimum voltage we just talked about. This one little number tells us the level of non-uniformity across the stack. And that, my friends, is our most powerful clue for figuring out exactly what's going wrong. Okay, we've got our clues. Now it's time to do some real detective work. Let's use these metrics to identify the unique fingerprints left behind by our 2 main culprits, flooding and dry out. First up, let's examine the crime scene for case number 1, flooding. This is what happens when a cell starts to drown in its own water. Now, take a look at this graph. This is the chaos of flooding, captured perfectly. See the blue line? That's our average voltage. It's dropping a little. But now look at the orange line, the minimum cell voltage. It's going completely haywire. It's plummeting and bouncing all over the place. And because of that, the green line, our delta, just explodes into this massive growing gap. That right there is the smoking gun for flooding. So let's just recap the evidence for flooding. First, the weakest cell's voltage just takes a nosedive compared to the average. Second, that delta, the gap between them, gets huge and unstable. And third, the whole system starts showing these wild, erratic fluctuations. It's a crystal clear sign of a localized problem. All right, now let's look at a totally different picture. Case number 2, dry out. This is what happens when the cell's membrane starts to get dehydrated. The difference here is just night and day. Look at the blue and orange lines, our mean and min voltages. They're falling together, almost in perfect harmony. The decline is smooth, no crazy oscillations. And most importantly, look at the green line, our delta. It's tiny and it's stable. that gap isn't growing at all. So the fingerprint for dryout is completely different. The mean and the minimum voltages drop together. The delta between them stays small and steady, and the whole decline is nice and smooth. This tells us it's not a localized issue in just one cell. It's a uniform problem that's affecting the entire stack in the same way. Okay, a correct diagnosis is fantastic, but it's pretty useless if you can't prescribe a cure, right? So how do we turn all this detective work into a practical solution that can actually save the fuel cell? Well, it really boils down to a super fast 4-step process that can all happen in milliseconds. Step 1, acquire the data from the CVM. Step 2, the system instantly computes our 3 key metrics. Step 3, it analyzes that all-important delta value. If it crosses a certain line, an alarm gets triggered. And finally, step 4, it acts, telling the fuel cell's control system to apply a fix right then and there. And here is the prescription. It's beautiful. If the system diagnoses flooding because that delta value is huge, it can automatically increase the airflow to help clear out all that excess water. But if it diagnoses dry out because the delta is small but the overall voltage is low, it can increase the humidity or just ease off the electrical load to give the cell a chance to recover. It's a direct, automated response based on our CVM clues. The source material really sums it up perfectly here. Flooding causes a localized loss, which creates a big difference among the cells. Dry out causes a uniform problem, which creates small differences. It's the type of difference that gives the whole game away. It's really that simple and that incredibly powerful. And that kind of brings us to a really fascinating thought. We've just seen how we can listen to the individual components of a complex energy system in real time. So if we can hear every single cell and respond instantly to what it needs, what does that mean for the future of energy? Could we be on the verge of building a truly failure-proof system? Now that is a question that could change everything.